Get rid of this thing. Yeah,
That bar at the top,
yeah.
it's like Control Alt Shift H or something funny like that.
All right, well, it seems to have disappeared. All right, so I'll talk a little bit about, some work that's been ongoing for several years now with a few, collaborators at various places. Here mainly with my grad students, Worcester Polytechnic, with one of my main colleagues here, Adam Sales, and also Luke at Harvard. Please feel free to jump in with questions at any time. Okay, so yeah, okay. So I'll start off just by giving some examples and motivation of what we're working on. Then I'll talk about our overall approach and then give some results at the end. So here's one example, and probably our biggest motivating example is this computer tutor program called Assistance. This is a tutoring program, computer-based learning platform, mostly with the focus on teaching mathematics, and it's used by about 500,000 students across the U.S., both for classwork at school and also for homework at home.
Is this elementary students?
Middle and high school mostly, yeah. And here's a picture of Neil, one of our collaborators who developed Assistance, and here he is showing it off at the White House. Right, so it's kind of, it's special as far as computer tutoring programs go, and why is that? Mainly because it has this thing built into it called the Assistance Test Bed, where independent third-party education researchers can propose various modifications to the curriculum, or just how it's implemented, and then check to see if it works. So you can think of this as being an integrated A/B platform. Someone proposes, well, here, I'll give the next slide, but it's active. There's been over 150 experiments so far. And one example would be, if I want to see, if a student gets stuck and I want to give them a hint, should that hint be a little bit of text to read, or should it be a video? So that's the type of question that gets built into these test bed experiments. And a typical outcome would be, does the student go on to complete that skill builder? And in a typical experiment, there will be a few hundred students, and it's student level randomization. So for this particular experiment, the results are that in the video condition, 83% of the students completed it. In the text condition, 73% completed it. And then if you look at your effect estimate, so 10%, but the confidence interval here is pretty wide, plus or minus 8%.
So can I back up for a second?
Oh, yeah.
So you've got this platform, it's an educational platform, and people want to make their own educational curriculum for that, right? Is that what and these are experiments to see which are the best prompts for them to use?
Yeah, by and large, the curricula exists, but then people will want to tweak it in various ways and see how those tweaks play out.
So this is like analyzing a prompt, a tweaking on a prompt for this.
Yeah.
Got it, thank you.
Yeah. So this is just kind of pointing out, and this is kind of a universal thing with reasonably small experiments, you end up with a pretty big confidence interval on your effect estimate. Okay, so what can we do? Well, we start thinking about it. We realize we've got a whole lot of nice covariate information on the students using this platform. So for each student, we have log data, and so for each previous skill builder that the student has done, we've got whether they completed it, the number of problems they attempted before mastery, and then we also have a bunch of demographic data. We also have a really nice auxiliary data set, which is observational in nature, and it's basically all of the students in assessments who were not randomized. So not the 447 that were part of this experiment, but everybody else. So this might be previous users, or it could be current users that weren't assigned to this particular skill. And for all of these students, we have the same covariates available. Okay, so that's one motivating example. Here is another one, an effectiveness trial. Another tutoring program called Cognitive Tutor Algebra. They wanted to test to see how well it works. So it's a computer program. It also has some alternative curricula associated with it, and tested it out in some schools in Texas. And then there's a trial to do this involving 32 middle schools and 12 high schools. The outcome in this case was the passing rate on a standardized test in Texas. And here are the results. The effect estimates on this passing rate and the confidence intervals. And again, really the takeaway here is just that the confidence intervals are so wide as to be to make the results somewhat uninformative for policy. Okay, again, we've got some very nice covariate data. In this case, we've got school level data from state administrative databases with about 4,000 covariates on each school. And we also have, again, a very nice auxiliary data set that's observational in nature. In this case, would be that same administrative data, but for all of the other schools in Texas, which is another 1,800 middle schools and 1,500 high schools.
4,000 covariates.
Yeah.
4,000 covariates. Is that possible?
Yeah.
What kind of, how could you even measure that?
Yeah, a lot of it is
No, it's just, I got it's not.
various stuff over like
Not
that.
central.
It's about like a few hundred covariates per year over several years. Yeah, okay.
Sorry.
I don't know. That's good. That was my reaction when Adam told me that. We were like, what? What is all this stuff? But yeah, you look through it and various combinations of things, and sure enough, you have 4,000 in there. Anyway, so here's the big question that we're going to be looking at is, can we use all of this auxiliary data? So kind of the first instinct is, oh, there's so much of it, such a huge sample size. And we've got really rich covariates. But on the other hand, all of this auxiliary data, it's not randomized. And so in other words, not randomized for treatment or control. And beyond that, this auxiliary population might be systematically different than the RCT. So this kind of brings up differences between experimental and observational data just in general. I'll kind of summarize. In randomized trials, they are very nice because you don't have to worry about confounding. That's the main reason that they exist. Also very nice because they allow you to do design-based analysis. I'll say several slides from now a little bit more exactly what I mean by this. But on the negative side, very often you're dealing with relatively small sample sizes. To contrast with observational studies, you typically have to worry about confounding. To deal with the confounding, you often end up doing some sort of model-based analysis, which involves various modeling assumptions. But on the plus side, you often have a very large sample size. Okay, so what we're hoping to do is to, at least to some extent, get the best of both of these worlds. And the very specific question that we're going to be asking is, how can we use the observational data to improve the precision of the RCT? So just a little bit of related work about joining observational and experimental in general. Goes back several decades. And it's still, there's been some pretty exciting recent stuff. A lot of the recent stuff, is geared towards a slightly different problem than what we are working on. More focused on if the RCT, is systematically different than the population at large, can we improve the, external validity, generalize the results of the RCT back to larger population. Again, what we're doing a slightly different take, which is to improve the precision of the RCT. And there's a little bit of related work on that, using observational data to improve the precision of RCT. A lot of it is in online computer experiments. Okay, so I've got the slide that I call our mantra, and this kind of sets out what our overarching goals are as we go about trying to do this. And basically, first, do no harm. And what I mean by that in particular is that, so again, randomized experiments are very nice in that they give you these unbiased estimates, and allow for design-based inference. And we want to maintain these advantages. So the first and foremost thing that we don't want to do is allow any sort of biases from the observational data to leak into our final estimate. Again, our goal here is to improve precision. That's the point of bringing in the observational data. So we want to make sure that we actually don't end up accidentally hurting precision. And then finally, we don't want to have to introduce any additional modeling assumptions. So again, one of the very nice things about randomized trials is that you don't need any statistical modeling assumptions, and we want to maintain that. Okay, so especially talking about not having any modeling assumptions and what I mentioned earlier about design-based inference, I'm gonna give a couple slides just to say really explicitly what I mean by that. Yeah. Okay, so design-based inference, that just means that it's the physical randomization that largely justifies the statistical analysis. And the treatment assignment is often the only variable that is regarded as random in the analysis. So one example of this would be a permutation test. Another example would be the name and movement model, and that's what we'll be using. So in this model, we've got potential outcomes. So we'll have n participants, we'll have a treatment group and a control group. And let's just assume for simplicity, which is actually true in these assessment experiments, each participant is independently assigned to treatment with probability half. Okay, so now associated with each participant, we have an outcome, which might be, for example, the time to complete the skill builder. And to state what is maybe obvious, this outcome might depend on the treatment. So another way of saying this just a little more explicitly, if the coin had landed the other way, the outcome might have been different. So associated with each participant, we actually have two potential outcomes. The outcome that would happen if you put them in the treatment group, and the outcome that would happen if you put them in the control group. Of course, we only ever get to observe one of them, because we either put them in treatment or we put them in control. And the other counterfactor. Okay, so formalizing this a little bit, just with some notation, for each participant I, we've got two potential outcomes, YIP and YIC. We are going to think of these as fixed values, not random. Or another way of saying this is we're going to think of the YIT and the YIC as very much intrinsic properties of each person and can be arbitrary from one person to the next. So not necessarily part of any larger distribution. Capital TI, that's going to be the treatment assignment. It's going to be 1 if you end up in treatment, 0 if you end up in control. And YI is the observed outcome for person I. So if you end up in treatment, you get to observe the treatment potential outcome. If you end up in control, you observe the control potential outcome. And this is a compact way of writing that out.
Is there any consideration of the counterfactual in doing any of this?
How do you mean?
Hmm?
What do you mean?
You made reference to a counterfactual
Mm-hmm,
that you don't observe.
mm-hmm.
And so I'm wondering if you take into account what's not observed in the process of thinking about the observed items as well.
I think the answer is yes. Let me go another slide or two and no. Just let me go another slide or two and I'll ask you if I've yeah.
So there's no, within person variability, is what you're saying.
Within person variability.
You say you observe person,
Mm-hmm,
an outcome for a person.
mm-hmm.
If you observed it the next day, it would be the same.
We're not saying that.
There's no within person variability, there's just between people variability.
So we are saying that each person has one fixed YIT and one fixed YIC.
Oh, yeah.
If we were thinking about like giving the same person the same test, same assignment like on different days, then you would think of having a different index for the different days.
Okay.
So yeah, this is kind of like the outcome that this person would have when you gave them the test at that specific point in time, and so on. And if you want to think of these as there still being some random element to it, because they're at home and maybe something happens at home or that distracts them or maybe not. The way that this is traditionally thought about is that you condition on that person's, like, so if you think of that, their outcome is their treatment potential outcome as being random and their control potential, you condition on it. Okay, so we're now going to define an individual treatment effect, which is the treatment potential outcome minus the control potential outcome. And this is just, well, again, this is the definition of the effect of the treatment on person I. So each person has their own tau I. And that maybe already answers your question, does it?
I'm thinking about it, so thank you.
Yeah, okay. So the treatment effect is defined in terms of both potential outcomes, only one of which is observed. So as a result of that, the individual treatment effect itself is never observed. We get to observe either this potential outcome or this potential outcome, but we don't get to observe both, so we don't get to observe the individual treatment effect. But we do suppose in some sense that it exists. Yeah.
I'm sorry, still not clear for me. So is each of these potential outcomes a random variable by themselves, or are they deterministic and the only random part is the treatment assignment?
The latter. Each person has two fixed potential outcomes, and the only random part is the treatment assignment. And then the average treatment effect, that is just defined as the average over all of the individual treatment effects. And this average treatment effect can be estimated. Just note that the average treatment effect is the average of all of the treatment potential outcomes minus the average of all of the control potential outcomes. And that the average of the treatment potential outcomes and the average of the control potential outcomes can both individually be estimated because we observe a random sample of the treatment potential outcomes and we observe a random sample of the control potential outcomes. So it's basically just a sampling argument. Okay, so that brings us to the simple difference in means estimator. Let this T and the C denote the indices of the treatment and the control units. And then N is the number of people that end up in the treatment group. Then the simple difference in means estimator, that's just the average of everybody in treatment minus the average of everybody in control. And this difference in means estimator is unbiased, again, just by simple sampling arguments. Okay, so again, going back to our mantra, I said I don't want any possible bias to leak in because we're using the observational data. We want to actually improve precision, or at least not harm it. And we don't want to introduce any modeling assumptions, by which I mean, I don't want to assume anything beyond what I just had in these last few slides. Okay. Any questions there? Do you feel like I've answered you
I
yet?
think so,
Okay,
thank you.
yeah. Okay, so in the next couple of slides, I want to just point out that this is possible, at least. And I'm going to show this method called residualization, which has shown up recently in a couple places. And it uses machine learning to basically predict outcomes from covariates. You can think of the observational data as being a training set, and the RCT as being a target set for the predictions. The basic idea is that you then residualize the observed outcomes to the predicted outcomes, and then proceed to perform your analysis on the residuals. So here's kind of a picture of this. You've got the huge database. You have the randomized trial performed on a few people within the larger population. And step one, you train a model to predict outcomes using the observational data, but not using the RCT data. So you set some sort of model to predict outcomes from covariates. You then take that model and you apply it to everybody in the RCT, so that you have predicted outcomes for everybody in the RCT. And then you residualize, so subtract off the predicted outcomes from the actual outcomes. And then you perform your analysis, the difference in means, on the residuals rather than the original outcomes. So in showing this in some formulas, so we define the new outcome as this residual, which is the original outcome minus the predicted outcome. And then we can actually start thinking about potential residuals. So if the person ends up in the control group, we would see this residual, the control potential outcome minus this predicted outcome. And if they ended up in treatment, you'd see this treatment potential residual, which is the treatment potential outcome minus the predicted outcome. And the key thing here is that the treatment effect on the potential residuals is the same as the treatment effect on the original potential outcomes, just because the prediction does not itself depend on the treatment. So then you can go and you can estimate your effects on these residuals instead of the original outcome variable. And with any luck, this will reduce standard errors. In particular, if the variance across individuals of the control potential residuals is less than the variance across individuals of the original outcomes, and same for the treatment, then this will reduce your standard errors. But if this predicted outcome is a poor prediction, you can actually end up hurting things.
So it's a
So
function of the model that you train.
yeah, so
That's where the residuals rise.
yeah, so if you have a bad model, you can hurt things. So summarize, this approach, it can help the precision if the predictions are good, but it can harm precision if the predictions are bad. And in practice, what this means is that the experimental group must be reasonably similar to the observational population, so that your model actually extrapolates well to the experiment. So thinking about this in terms of our mantra, we're still guaranteed to be unbiased. We haven't introduced any modeling assumptions, but it is possible that we'd end up harming our precision instead of helping it.
The whole zillions of covariates are supposed to help with precision, right? To help make the predictions from the observational data better or help. They're supposed to help with that, aren't they?
Yeah,
Have these zillions of covariates, they better do something.
yeah.
I guess sometimes they don't.
Right, well, but the biggest concern is that the RCT is systematically different, that the people in the RCT are systematically different than the people in the rest of the data. And so
The covariates might help fix that to some, no?
well, to some extent, yeah, I mean, it depends on the nature of the systematically different,
Okay.
yeah.
That's all the problem with experiment, well, it's often a problem with experiments, and that the people who agree to be in your experiment are not representative of some larger population that you're interested in.
Yeah, yeah. We're actually a little bit lucky in this case because the students aren't opting in or opting out. But it's still an issue. I mean, yeah. Yeah.
So the goal is to use prediction model to try to reduce errors.
Mhm.
So in that way, can I use this variance reduction to try to train my prediction model? Right, so because always, if a prediction model is zero, the same variance as original. But if I try to minimize variance, try to come up with prediction model, instead of manually doing two steps, we use observation come up with prediction model, and carry the procedure. But it's the only way I can just target for variance reduction, try to train a prediction model with that. That makes sense?
Can you say it one more time?
Yeah, so I can read, well, right now prediction is to try to come up with a prediction model, but if my goal is try to reduce variability, I can set my variability as my object function, try to find what's the prediction.
Oh, you mean the variability in the RCT?
Yeah, in a residual.
Okay. So the issue there is this argument is based off of the model or basically you can't touch the outcomes in the RCT, otherwise you'll introduce a bias.
I know, but I use this variance for RCT and then try to train my hat the function for this observation data.
But to get this, you need to look at the outcomes of the RCT.
You mean try to estimate this variance?
Yeah. I think, unless, did you have a different way of estimating it?
So you train the first model by minimizing the variance on the other set.
On the observational data.
Set.
Yeah.
So that variance is already minimized in the
Mhm.
training set.
Yeah.
And now you're saying, the next step you're saying is what?
Well, my study is instead of doing this, I train my model with observation data. But my model will be trained such that eventually this RCT variance will be smaller.
I got he wants to have a weighted variance trained model where the variance in the RCT mean is more important than a minimization.
Something like that. My hat is zero, it's very the same, right?
But
So that's one training, but I can use some other model, I can make the variance smaller.
But I guess my question is, how would you do that without looking at the outcomes in the RCT?
No, I only use the RCT outcome.
He has to.
The variance, right?
You have to look at the outcomes. So he's raising that as an issue. That you shouldn't be looking at those. Is that what you're saying?
Yeah.
It's true, the prediction model can depend on RCT outcome. But do you think that the bias and variance estimation?
That can introduce a bias, yeah. I can't say off the top of my head all the conditions in which it would introduce a bias versus those where it wouldn't, but it's certainly possible. Okay. Back till 7, right?
Yeah.
Yeah, okay. I think we're on track. Okay. I'm gonna shift gears a little bit and talk about what someone might do if they only had the randomized trial. And so we're putting out of our heads now for a minute any auxiliary data. So we're working only with RCT data. What might you do? So here also is a long literature of doing covariate adjustment purely within your RCT estimate. There's a paper that by Friedman that looks at what happens when you do this using OLS, along with some follow-up. But there are other approaches as well, such as the doubly robust estimator, and more recently, various estimators that use some form of sample splitting. In the next couple slides, I'm going to show how some of these sample splitting methods play out, and how they can be used to actually get you an unbiased estimate, even though they will, in their own way, look at the outcome variables in the RCT, basically because it worked out because we split. And in these methods as well, any machine learning prediction method can be used. So I'm gonna pause here for a second and ask you all a question. This tau I, this individual treatment effect, is that estimable? So, for example, is Chris's treatment effect estimable?
We can estimate it, but it won't have any good statistical properties.
I'm using estimable in the technical sense of meaning there exists an unbiased estimator for it.
Not for the average difference, but for the individual differences?
For the individual treatment effect. No? No? Okay, good. You're all saying no, which means you followed along well, but that's actually not true. So let me present this following estimate of an individual treatment effect. Basically, if you end up in treatment, take your outcome and multiply it by 2. If you end up in control, take your outcome and multiply it by -2. That's how you should be looking right now, and that's how most of you do look right now, which is good. So this actually is an unbiased estimate of the individual treatment effect. So if you now think about the expected value of this tau I hat, there's a 50% chance that you end up in treatment, in which case you take times 2 times YID, 50% chance you end up control times what you do then, and you actually end up with an unbiased estimate of the individual treatment effect.
What's T again?
The capital, this one?
Yeah.
Treatment assignment. Yeah, right. So see, it's a very noisy estimate, right? So that's the problem. It's unbiased, but you would not want to use this in.
It's not helpful.
It's not helpful, right?
It's just to prove something that's useless.
Right. Right.
And then any other.
Right.
Is that the case that usually there's some useless estimable construct or something?
No.
No, okay.
No. If you average across all of these, that will give you an unbiased estimate of the average treatment effect. But as we've kind of all agreed, this is not the most useful estimator. So can we make it useful? And what I'm going to do now is I'm going to define this quantity M, which is just the mean of the 2 potential outcomes, the treatment and the control potential outcome. And we're going to let this MI hat be an estimate of the MI. And for the moment, don't worry about where this comes from. It's just notation, MI hat, that's an estimate of MI. This is what MI is. And now I want to consider another estimate of this tau I, of the individual treatment effect. Very similar idea, except that we subtract off this estimate of the M from our outcome before doing what I said previously. And for basically the same logic, as long as this MI hat and the TI are independent, then the tau I hat is again unbiased. In fact, if the MI hat, if you get it right, exactly right, then your tau I hat has 0 variance. More generally, the variance of the tau I hat depends on the squared error of your estimate of the MI. And I've got I like pictures, so here's all of this in picture. So say we've got a situation where the control potential outcome is 4, the treatment potential outcome is 10. So the treatment effect, which we never observe, is 6. And this MI, which we also don't get to observe, is 7. So suppose that we were somehow able to have estimated this MI exactly, and we said that it was 7. Well, then if we end up in treatment, we get to observe this treatment potential outcome. We see that difference of 3. We double it and then come up with an estimate of 6, which is right. On the other hand, if we end up in control, our observed outcome is this 4. We look at this difference, which is 3. We double it, get 6, and again, which is right. So the expected value is 6. The variance is 0. If we were a little bit off, so we had guessed the MI to be 6, when in fact it's the 7. So if you end up in treatment, you get to see the 10, you get to see that 4, you double it and you get 8. On the other hand, if you end up in control, you get to see that 4, you get to see that 2, you double it, you get 4. In expectation, you're right. But now with a lot less variance. Okay, so this lends itself to a procedure. You've got here we're just looking at the RCT, you've got your treatment group and you've got your control group. Within each arm of the trial, within the control and within the treatment, in each one, you train an outcome model, leaving out I. So you train a model to predict the control outcomes from the control units, and you train a model to predict the treatment outcomes from the treatment. And then using these, you predict both the control potential outcome and the treatment potential outcome for unit I, average them, and that gives you your MI hat. So now you've got that estimate. This estimate is independent of everything else that happened in the treatment of the control group, because everybody's assigned by a coin flip, independent coin flip. And so then once you, now and only now, you look and you see that this person actually got assigned to control, and then you can calculate your treatment effect estimate for them. And then you just go through that person by person, and you get individual unbiased treatment effects for each person in the trial.
Does it matter that your predictions are correlated because they're built with basically the same data when you just sort of leave one out of the time?
It doesn't matter for the unbiasedness argument. It matters for when you go to estimate the variance. And it mainly matters in an annoying way because mathematically, under like very weak regularity conditions, those covariances disappear, but you still have to show it, which is annoying.
Okay.
Yeah. Okay. So properties. It's guaranteed to be exactly unbiased. Again, the only assumptions here are the random assignment and also no interference, meaning that one person's like the kids don't help each other with homework, basically.
Like unbiased.
Yeah. One nice thing is, okay, so you have to predict the treatment outcomes, and you have to predict the control outcomes, if you do the simplest thing, which is basically mean imputation, and then you do this entire procedure that I just described, that gets you exactly back to the difference in means estimator, which is nice. It means like if you do kind of the simplest prediction model, mean imputation, that gets you back to just the difference in means estimator. So all of this machinery doesn't cost you anything inherently, is kind of what this is saying. Yeah, so just predict the control outcomes as the average of all of the other control outcomes, predict the treatment outcome as the average of all of the other treatment outcomes. That gets you back to the difference in means estimator. The variance estimate also ends up to be nearly the same. This is under mean imputation. If you did mean imputation, the variance estimate ends up being nearly the same as if you just did the normal t-test variance estimate. So what this means in practice is that doing mean imputation basically reduces you back to the t-test, which is very nice, because basically what this is saying is if you can improve upon mean imputation, then you can improve upon the difference in means. And so basically what we've now given ourselves is just the task that we have to come up with a prediction model that does better than mean imputation. Okay. So going back to our mantra here, yeah.
When you say mean imputation, do you also do something like doing some combining rules? Do you like do it account for the imputation and variance? Or I guess I don't know.
For
example, so if I follow the framework of multiple imputation, for example, then I have like an outcome model that I estimate, and then I sort of, it's a Bayesian perspective almost, but I think, or it takes from Bayesian perspective, but the idea is that you just do one mean imputation, you're underestimating the uncertainty you have in those things that you've imputed. So you do it several times and you take, and there's a variance formulas. So I'm wondering, like, would you account for that in your mean imputation here?
No. Just quite literally, so, you know, thinking about this procedure, basically to get this in my hat, I need it's going to be the average of a predicted treatment outcome and a predicted control outcome. And the predicted treatment outcome is just the mean of all of these treatment outcomes. And the predicted control outcome is just the mean of all of these control outcomes.
Okay.
And then we get the variance in a different way.
So imputation is often thought of, in my vague understanding, is replacing missing values. In that, and in this situation, are you guessing at the mean? And is that what you mean by the imputation? You're thinking of everything is missing, or you're leaving out one of them and then you're guessing?
Yeah, for the purposes of this, it's basically thinking like before I look at any of the outcome on person I can think of person's I outcome as being missing.
Okay, and then guess the mean for them.
Yeah.
Okay. Then I see.
Right. So now we've again, we're still guaranteed to be unbiased. We still haven't introduced any additional modeling assumptions. We're not mathematically guaranteed to improve precision, but as long as we can improve on mean imputation, we will. But I still got to put this to yellow because at this point we haven't made use of any auxiliary data, and we still would like to. So let's bring that back in. And the basic idea that we're going to use is just that we're going to still use the auxiliary data to come up with a model for predicting outcomes. We're still going to compute those predicted outcomes for everybody in the RCT. But instead of subtracting them off, we're going to take these predicted outcomes and actually use them as a covariate in the RCT. Using a method like what I just described. So, way of thinking of this, so this predicted outcome model that's fit to the auxiliary data. So yeah, the model is trained on the auxiliary data. The covariates are all pre-treatment, which means that neither the model nor these covariates are affected by treatment. So the predicted outcomes for everybody in the RCT invariant to treatment assignment. So really, you can think of this as just any other pre-treatment covariate, and it might be a really good one, but of course it might not be too. Okay, so what we're going to do is I'm just going to skip to this picture. So the idea is we're going to train the model on the observational data. Then we extrapolate it to the RCT. So we have predicted outcomes for everybody in the RCT. And then using this kind of leave one out approach, we essentially recalibrate those predictions. So if this is mainly going to be an issue if the people in the RCT are systematically different than the people in the observational data, but using everybody except for I, we can recalibrate those control outcome predictions, and using everybody except for I, we can recalibrate those treatment predictions when predicting the outcomes of person I in the RCT. So that's the basic idea. Now let me go back to here. But one way a little bit more explicitly of doing this would be that within the RCT we use just a simple linear regression. So we get our predicted outcomes using the auxiliary model and applying it to the covariates of the people in the RCT, and then we use that to predict the ith outcome within the RCT. So these individual beta hats, those are fit using everybody but person I. And then same for the treatment. And one thing that you can see that's nice, if the slope coefficients are 0, that same logic as before, that means that we actually end up getting back to the simple difference in means estimator. If the slope coefficients are 1, that gets us back to this residualization estimator. But we're getting these slopes empirically. They could be anything between 0 and 1, depending on how useful these covariates are. So you're basically adaptively deciding how much to use these predictions. If they're really bad, you don't use them at all. If they're good, you use them a lot. And that, again, that's kind of what's happening here.
But if the intercepts are different, then you get the bias, right?
If what now?
If the intercepts are different, then you'll get your bias.
If which intercepts are different? Well, the answer is no, but which intercepts?
The beta zeros in your formula. Beta sub zeros. Those intercepts, if they're different, then you're.
No, because the unbiasedness comes from, so however I get this predicted YIC and however I get this predicted YIT, the unbiasedness comes back from, well, this whole thing. It comes from the random assignment of person I.
Right.
Yeah, so those
I'm
intercepts.
just subtracting the intercepts, that's all. You know, that's all I was doing. That's what we do.
Okay, so that's one idea. Basically, just recalibrating the predictions linearly. You could also use all of the other covariates that are in the RCT, and that would be especially helpful if the RCT participants actually are systematically different than people in the auxiliary population. Maybe using the covariates within the RCT ends up being your best bet. So that would be another option. But that wouldn't necessarily be better if the auxiliary based predictions are really good, and you've got a small RCT, then it might be too hard to really get a good estimate using, and if the covariates are high dimensional, it might be hard to get a good estimate using, predicting just with the experimental data. So you've kind of got these two opposing regimes, so you could also try and do a weighted average of these two. And this will be an ensemble approach. So going back again to our mantra, at this point, we've guaranteed no bias leakage. We're not using any additional modeling assumptions. And as long as we don't do anything too crazy, which is pretty easy in practice not to do, we'll end up either improving precision or at least not hurting it. Okay, so here's some results. Going back to the assessments experiments. Again, we've got this auxiliary data, tons of students in it, log level data, demographic data. We trained a neural net on it. Won't go into details on that, but we got some pretty good predictions out of it. So here are a couple plots. Here is a plot comparing the difference in means estimator versus that first residualization estimator that I showed you. What's being plotted here is the relative ratio of the effective sample size. So there's 33 dots here for 33 different experiments that we analyzed. And this dot, for example, is basically saying that for this experiment, doing the residualization increased the effective sample size by nearly a factor of 2 relative to the standard difference in means estimator. And so what we see here is that very often the residualization helps, but in some cases it can actually quite hurt too.
Or two in the other direction.
Yes. Here, I'm comparing difference in means to this recalibrated estimator. And now, as promised, you basically improve your effective sample size, or you at least don't hurt it. And then this is comparing more explicitly the residualization to the recalibrated, and we see that this recalibration pretty much always helps us. Okay, good. Here, so now comparing the recalibrated estimator versus the ensemble. So this is basically showing us that also throwing in the within RCT covariate data can help us even more. This is comparing if you used only the within RCT covariate data, so you ignored all of the auxiliary data to our ensemble approach. This is showing that typically the ensemble does better, and this basically is the plot that shows that the auxiliary data is still helpful even when compared to methods without the best of methods without the auxiliary data. And then this is just kind of at the end of the day, how much do we actually do better than difference in means? And we see potentially quite a bit. So this is our ensemble estimator, which is our recommended one, being compared to the difference in means. We see that for some experiments, we increase the effective sample size by a factor of 2 or even more. And most importantly, we never hurt. At least most importantly to me. Okay, good. Here's the effectiveness trial in Texas. Again, this is where we had school level randomization to see the effectiveness of this cognitive tutor algebra program. There's 44 schools. This is a story in and of itself, but it's a paired design here, so you have to rework some of the methodology for that. So that was our auxiliary data. Here again, looking at effective increase in sample size. So one natural thing to do would be to just use each school's previous test scores passing rates and just do a diff and diff. And that already gets you an improvement of 68% relative to doing a difference in means without doing diff and diff. If you wanted to try and do an analysis where you threw in all of the covariates, and you're imputing via random forest, even though this includes the previous year's test score, you end up not seeing the improvement that you would like to have seen, because with the small sample size of 44 and the 4,000 covariates, the random forest just does not do a good job of picking out the previous year's test score as the thing to use. So you actually don't get the gain. But if you use the auxiliary data, and you've trained the model on all of the covariates in all of the schools in the auxiliary data, and then do the recalibration approach, now you've increased your effective sample size by 155%. All right, so that's basically it. And let's see, did I? Yeah, okay. So just basically the takeaways here. This is the biggest one, that this can and I think should be done, that you can use auxiliary data to improve the precision of randomized trials with very few downsides. There's basically nothing to be lost by doing this. And we've kind of demonstrated this by taking this first do no harm approach. And I guess I'll point out here also that this is also especially important when you want to set your analysis protocol in advance, which very often you do, so that you don't end up data snooping. You want to put into your analysis protocol something that you're pretty sure will actually, at the end of the day, be helpful or at least not harmful. The auxiliary data, I didn't talk about this too much, but because it's kind of its own separate data, and you can do whatever sort of modeling on there you want, you can really go to town on the auxiliary data and treat it as kind of like a modeling sandbox. You can try out all the different models you want, try out neural nets, random forests, or whatever, and then go with what really seems to be working the best. So you don't need to worry about data snooping in terms of model building on the auxiliary data. And then of course, none of this is limited to education. You can imagine doing this stuff with, say, clinical trials and electronic health records, or various other fields as well. Yeah.
Are there no assumptions on the MI that you use to improve your estimation?
For the unbiased argument, no, nothing. Well, other than it's that the estimate of the MI is independent of I's treatment.
Okay, but so that means that if I pick one random number from rolling a dice, that still improves, or it's still not worse than the.
That won't help you in terms of precision, but the unbiased argument will still hold.
Okay, but there are assumptions that you need to hold in order to improve the
So
precision.
in order to improve the precision, you need to have a mean squared error of your predictions that is less than the mean squared error that you would get by mean imputation.
So any estimator or any tool that we use to get M that fulfills this improves our precision.
What would be a worst case scenario? Let's say your auxiliary model, you just completely overfit it, and you come up with a piece of garbage for the auxiliary model. Is that, I mean, can you actually do worse with
Not really, not substantially. What would happen then is, so if your predictions basically end up being noise, then when you go to do this recalibration step, the slope there will basically be zero. Will basically be, there's no association between the predicted outcomes and the actual outcomes in the experiment. That slope will basically go to zero, and then you can show mathematically, if these slopes were identically zero, it gets you back to the simple difference in means estimator. So the worst that would happen is that they wouldn't be identically zero, they'd be zero with a little bit of noise, and that little bit of noise would add a little bit of noise, and so you do ever so slightly worse than the difference in means estimator, but not by much.
Okay, like I guess that one example where it was 1%, was it 1% worse?
Yeah,
And so,
that's this phenomenon happening.
and so have you like constructed pathological cases to see like, you know, is there like, can you put a bound on how much worse it could be? I mean, not that it really matters for a practical standpoint. But...
I mean, no, I don't think you can put a bound on it. I mean, if you get the sample size small enough and you get the, I mean, just imagine that your sample size is 3 and you've got it, and you know, you've got to be doing this leave one out thing. So you can imagine that for 2 of the 3 things work out perfectly, and then the third one is way off. And so when you drop the 1, you'll think that you're doing great, and so you'll predict. But yeah, so you can definitely construct a pathological case, especially in small samples, where you'll get worse. But again, the practical answer is that if you can do the leave one out mean, or the leave one out imputation with lower MSE than leave one out mean imputation, you come out ahead.
Sorry, this is so late.
Oh, thanks. Yeah.
So, a lot of cases in the observational data
Mhm.
also have treatment
Have what?
have treatment information.
Mm-hmm.
So in that case, how you going to do this kind of prediction? Do you want, well, I understand you should use all the data, you can more treatment information, but can I just use control mode, come up prediction model, or use treatment mode, come up prediction model, and take something like a weighted average? Do you think it will be better compared to just ignore treatment information to come up prediction model?
So you're saying come up with a treatment model in the observational
But
data?
there's a treatment information,
Mhm.
right? So, if you take this, well, unbiased, take a drug one, drug 2.
Mm-hmm.
So right now you come up with a prediction model by hand, you just ignore the drug information.
Yeah.
Do you think it's reasonable, or I don't know, let's reasonable, see, I only use drug 1 to come up with prediction model, or drug 2 to come up with or use some weighted average. You know, prediction. Do you think it's different?
It depends a lot on your level of treatment effect heterogeneity.
Yeah, that's what I feel.
Yeah.
It depends on how big gap that they are.
Yeah. Uh-huh.
Is there any way, like say, I use that from real model, I come up with estimate, surely that, and that should mean that can we repeat the observation data come up better prediction model? Based on what I just described.
So I mean, so what you could
Well, of course, it depends on the common.
yeah, so what you could do is for each person, you could produce a predicted treatment outcome and a predicted control outcome. And then when you go to basically this, so when you do this recalibration step, you could choose to do that only based off of the predicted control outcomes.
Yeah.
And do it here based on only and you're right, you might end up doing better if you did, and this would depend on the level of treatment effect heterogeneity. You might want to just use the predicted control outcomes, or you might want to use a weighted, and you could, as long as this is getting to moderate sample sizes, you could even, presumably pick that weight, as long as you pick that weight using only this leave one out data.
Or can we like put who predict the outcome?
Mhm.
Like travel, like have to put it into the question.
Mhm.
I think
Mhm.
it's the averages.
Mhm. Yeah,
Your third bullet point was about at the end was, you have a sandbox you can play in for the Y hat. And you still need to be a little bit careful that you don't take all your different modeling sandboxes and see how you do with your prediction at that point and choose the one with the smallest precision or the tightest bound. I mean, it seems to me that you can do lots of Y hats, and as long as you stop at the end of your auxiliary data and pick one.
yeah,
And then you want to look at the experimental data, and you don't want to.
right, sorry, I should have said that explicitly. Yeah, as long as you do not look at the RCT data, you can do whatever you want with the auxiliary data, yeah. You only get to look at the RCT data once, yeah, yeah.
So the white hat that we use, that can be biased and it can be, you can use all of the X's in whatever crazy ways that I think it can be used and still tell you no worse. Oh, this is great.
Well, he made allusion to if you use an overfit model, you'll get a lot of noise. That's,
You get a lot of noise in your predictions, but then, you wouldn't necessarily end up doing any worse with your final estimate.
any worse,
Yeah.
right?
Mhm.
Yeah.
You can even, here, just it's really kind of funny to think about, if your predictions are systematically wrong, so like they're anti-correlated with the outcome, well, then those beta hats end up negative and you actually still come out ahead.
Yeah.
Yeah.
Never get there, you see less than 0.5.
Yeah. With Corey, yeah.
So I was just gonna ask, so suppose you are designing a clinical trial and you come up with a sample size using some naive analysis.
Oh, yeah.
And you say you want to use this auxiliary data,
Mhm.
create this auxiliary model and supplement it. How would you estimate how much you would reduce your sample size by? I mean, is there a tool or? do you have to
I
trust
have a PhD student who's about a week or two away from finishing a shiny up on that.
Oh, cool.
Yeah. But basically the idea is well, in this tool, it throws a random forest at the auxiliary data, looks at the MSEs, and then also looks at the MSEs for various subpopulations within the observational data to give you kind of a sense of like if your RCT was this weird subpopulation, your MSE might be this high, and if your RCT was this other subpopulation, your MSE would only be this, and so the ranges of improvements would be this, and so you get a range of potential sample sizes depending on how weird your RCT might be. Unfortunately, that's not really a thing that you can predetermine, but you can still get a range of things in this way.
Well, thank you, that was,
Thank you all again.